This video is what you have been waiting for. We will combine all the knowledge acquired in the previous sections and add some general guidelines in order to design your very own PV system. Let's start with the design guidelines of a grid-connected system. We have seen this diagram of a grid-connected PV system before. As the name suggests, the PV system is connected to the electric grid. There is a continuous exchange of power with the electric grid via the distribution panel. As discussed before, the grid-connected PV system has these important PV system components. The PV array is an interconnection of modules that supplies the required photo-generated power to the system. The power rating of the array is determined based on the system design. The grid-connected or grid-tied inverter is the backbone of the grid-connected PV system. It is the inverter that is responsible for not only supplying power to the grid as a current source, but also for tracking the grid voltage and frequency. The grid and the load are usually connected through a distribution panel. The interaction with the grid is two-way. While the interaction with the load is unidirectional, a net meter is usually found in this type of PV system. A net meter is nothing but a two-way power measuring instrument. This meter takes into account not only the power consumed from the grid by the consumer, but also the power fed to the grid by the PV system. Now we will look at the important concept of system efficiency. We know that the solar to electricity conversion efficiency of PV modules could be as much as 20%. We have also seen how the efficiency of rest of the system components is less than 100%. To find the overall system efficiency, we will walk through the system to see the efficiency loss at each stage. Let's assume a solar spectrum of 1000 watts per square meters. The PV array is 20% efficient. Therefore, the power density present at the output of the PV array is 200 watts per square meter at maximum power point operation. The balance of system could be placed at a considerable distance from the PV array to protect the inverter against the weather conditions. In this case, the DC losses might be significant. Depending on the length of the cables and the amount of current through them, this loss could be around 1 to 2%. So in this example, we will assume that the cables have a transmission efficiency of 98%. Therefore, the DC power per area going to the inverters is 196 watts per square meters. Now, let's go to the inverter. With advancement in power electronics, it is rather common to have inverters that reach a DC to AC conversion efficiency greater than 97%. However, usually the efficiency of the inverter is dependent on the power at which it operates. For the sake of simplicity, we shall assume an average efficiency of 95% for the inverter. Thus, the AC power per area present in the system is 95% of 196, which is 186.2 watts per square meters. Assuming a lossless exchange at the distribution panel and dissipation in the cables carrying AC power that can be neglected, we get an overall PV system output of 186.2 watt per square meters. This means that the incoming irradiance at 1000 watt per square meters is processed by the PV system to give 186.2 watt per square meters. In other words, the overall system efficiency is 18.62%. It can also be said that the overall system efficiency is calculated as the product of the various component efficiencies. That is, eta system equals eta PV times eta cable times eta inverter. Now let us move to the design of a simple grid-connected PV system. Consider the same load demand as shown in the standalone PV system design example of the previous block. The required quantities of each kind of load, along with the duration of usage, are mentioned. The total power and energy requirements have been tabulated here as well. The only difference here is that there is no concept of autonomous days, as there is no storage. Instead, the electric grid acts as a limitless storage. Next, we consider the irradiance. Going by the same example as in the standalone system case, a location in India is considered with an average of 4.5 equivalent sun hours. Let's look at the electrical specification of an available PV module. It's a 240 watt-peak rated module with the given voltage and current parameters. Now we need to find out how many of such modules are required to power the loads. Assuming that the panel would be operated at its maximum power point, we can find out the required number of panels as follows. We can first calculate the amount of minimum PV power required by dividing the total energy demand with the equivalent sun hours. As a margin for system losses, the minimum power required could be 20% more than this ratio. Thus, the minimum PV power required is 480 watts. From this, it can be concluded that two 440 watt-peak modules are required to deliver the 480 watts power requirement. In grid-connected PV systems, it is usually seen that the inverter is sized based on the PV array sizes and not the load size, like in the standalone system. So the required PV power is 480 watts. The inverter should be able to handle this power. As a safety margin, generally the inverter is rated for a maximum of 20% higher than the PV array power. In this case, the maximum power rating of the inverter turns out to be 576 watts. Now let's take a look at the standalone or off-grid PV system. It is also called the off-grid PV system simply because it's independent of the electric grid. As discussed before, the standalone PV system has these important PV system components. Of course, there is a PV array. But now we also have to take storage into account to become truly independent. The battery bank is the lifeline of the standalone PV system. Without the battery, the system would be unable to meet the load demands during nighttime. The charge controller is responsible for ensuring a smooth functioning of the battery. The functioning of a battery is very complex. That is why the use of a good charge controller can increase the lifetime of the battery bank. This is more than welcome, as the battery lifetime often is a lot shorter than that of the PV modules. For a standalone inverter, the rule applies. The better the inverter, the higher the efficiency over a variety of loads. Together, the charge controller, battery, inverter, distribution panels, and the wiring make up the balance of systems. In general, everything in the PV system minus the PV array constitutes the balance of systems, or BOS. A standalone system could be connected to both DC and AC loads. Of course, the DC loads would be powered by the DC power before the inversion stage. Now let us first size the charge controller. The maximum allowable current and voltage rating can be found by assuming the worst case scenario. If the two modules are connected in parallel, then a maximum current of 2 times the short circuit current is possible, which in this case is 12 amperes. On the other hand, if two panels are connected in series, then a maximum voltage of 2 times the open circuit voltage is possible, which will equal 120 volts. Now let's look at the specification of an available charge controller. The operational voltage is the battery voltage that is supported by the controller. This is not to be confused with the maximum voltage, which simply specifies the amount of maximum voltage that it can handle at the input as provided by the PV output. We see that the maximum allowable voltage is greater than the series limit of 2 panels of 120 volts, while the maximum current doesn't support the parallel configuration current of 12 amps. So we select the series configuration of the panels. In general, given a choice between series and parallel, series configurations prefer to keep the current levels down, thereby minimizing the DC cable loss. Also, the charge controller can work in either 12 volts or 24 volts. It's beneficial to use 24 volt as the operational voltage because a higher voltage would ensure a smaller current for the same power. We are moving on to the battery. A single battery is given with the specification as shown. The depth of discharge, or the DOD, is the depth until which the battery can be effectively used. We must now choose how the battery bank must be configured. That is, how many batteries of the given specification should be there in the battery bank and how should they be interconnected. The minimum battery capacity can be derived as follows. Based on the operational voltage, depth of discharge and energy demand, the battery capacity can be sized as follows. Note that the days of autonomy and the system losses tend to increase the battery bank size. Also note that the lower the battery depth of discharge, the higher the battery bank capacity requirement. On the other hand, the higher the battery depth of discharge, the battery can be discharged more and therefore lower the battery bank capacity needed. So this gives us a minimum battery capacity of 300 amp hours. Now this brings us to the number of batteries required. An operational voltage of 24 volts requires 2 batteries of 12 volt each in series, whereas a battery capacity of 300 amp hours requires 3 batteries in parallel. Therefore, a total of 6 batteries are required such that they are in series to create the battery bank for the PV system. It's time for the inverter sizing. An inverter is available with an efficiency of 96% and operational voltage of 12 or 24 volts. What should be the minimum nominal power rating of this inverter? We know that the power demand of the load is 300 watts. Given the rated efficiency of the inverter, we can estimate the minimum nominal power rating as 312.5 watts. Note that the inverter may be less efficient than the rated efficiency, and under such conditions it's safer to have a margin for the power rating of the inverter. As you can see, there is a different way of calculating the inverter power requirement. In the grid-connected system, the inverter size was calculated with the PV array size at the core of it. Now the load power requirement is central in this calculation. Now you should be able to design your own PV system. The final question we will address is how expensive is this solar electricity? We will discuss that in the next video.